So, welcome to my presentation. Timber engineering, I would like to talk in the next few minutes about requirements, challenges, and the potential, not necessary in this order. Let's start here. I'm sure that all of you have already enjoyed wood in its most natural form. So maybe spending your free time in a forest, like I did on this very, I would say, typical Finnish autumn day with my kids. And you observe these advantages of having wood. I also think that most of you are aware of the advantages of using wood inside the building. Maybe some of you just enjoy the beauty of timber. Maybe others just like the living atmosphere that the room usually creates when it's surrounded by wooden surfaces. What you might not know is that you can also use timber or wood for structural purposes. And nowadays even for quite demanding structural purposes. So we are able to build nowadays large span structures, or like in this example, multi-story buildings. I would call this mid-rise, where the main load-bearing elements are wood or timber products. And this trend becomes popular due to multiple reasons. And I personally think it will also increase in the next decades. Let's maybe take a look why timber engineering becomes more popular. There are first of all advantages of timber itself. The list of advantages is of course much longer than these 3 bullet points here. The list is nearly endless, but I decided to pick up those 3. So the first one, it is a natural grown building material. And as such, it is very obvious that this will be one of the key players, the key contributors that we can achieve this green transition that our construction sector needs to do. For me as a structural engineer, it is also important to address that the mechanical properties of timber are also very effective. In particular, when you think about the properties, the strength properties of timber compared to its self-weight, it's outstanding. It can easily compete with materials like steel. A third point that I want to address here is its very high potential for prefabrication. Timber is light, timber is easy to work with, so we can easily transform the construction process towards prefabrication halls. There we can be much more precise, which really increase the quality of our product. I mean, we can do all of this in controlled indoor environments. And I think there's also a large benefit for our society because we can reduce the construction time, which is usually, when we have this in the neighborhood, quite annoying for all of us. But it's not only the advantages of timber that make this more popular, it's also technical developments that have been achieved. And also here the list is much longer, but I decided to pick out 3 points. First, engineered wood products. So in the last decades, there was a huge development of further engineered wood products, starting maybe with the most popular cross-laminated timber some decades ago, but nowadays more and more tailor-made products are available on the market. The next item is connection technology. This is most probably the most important driver during the last decades. So there have been huge developments to connect our elements better. I want to address 2, maybe closer. These are self-tapping screws and gluten rods, which really allow a much higher preciseness of our connection, much better mechanical performance, and therefore a better building quality. Maybe just to give you a figure about when I talk about the developments in connections, when we use, for example, screws, self-tapping screws in timber engineering, we don't talk about screws like this. We easily talk about screws with 1 meter length or something. So we really talk about massive volumes also in this case. A third item here I put is hybrid structures. In general, I mean, I'm a structural engineer, and as such, when we build, we should try to use always the right material at the right place. And when you look now at a timber structure, then I mean, at the end of the day, when you use the right material at the right place, we have to accept that every building that we build is a hybrid out of multiple materials. Timber is very very good in the combination with other materials. A very typical example, I already addressed connections before, is that most of our connections are performed with metal type fasteners. So that's a typical example where we combine materials. But here I pointed out timber concrete composites. That's slab systems where we make really hybrid for a floor element. The nice thing here is that we can utilize all the good advantages of timber and also compensate some of its weaknesses. The lightweight can be a weakness, or the acoustic performance, by just adding a very slim layer of concrete that is permanently connected. With all these advantages of the material combined with the technical development, the trend of building timber has continued, and I'm pretty sure it will continue. And now let's look maybe shortly what we require from a building, in particular from a structural point. And I think we can describe this with these two keywords. A building should be reliable, and we should use everything we use there should be efficient, and it should be functionally efficient. Reliable, I might don't have to talk so much about it. I think it's very obvious. I mean, we live in these buildings for decades, and we want to feel safe in this building. So the building has to be reliable. We want to use that properly. When it comes to efficiency, I maybe would like to talk a bit longer, because at the moment I think many people see efficiency in purely economic terms, and this is something I really don't like. So I think when we should talk about buildings that we should build efficiently, that we should really think about the amount of material that we're using. It was addressed before. We should consider the environmental performance a building has. We should also consider the living quality that we have in the building and the possibility to use it. I think we can also address issues like the construction speed. I think also when we build for the potential of adaptation, I mean maybe we have a change of use in 30 years. It would be nice when you have buildings that are able to adapt. The potential of repair a structure. Think about the local moisture damage somewhere in the middle of this building due to a sprinkler that went accidentally on. It would be nice when we design structures that are able to be repaired. And also the potential of reusing, that we design already building to reuse. And of course, one item in all these lists when we talk about efficiency of buildings is of course also, but not only, the price of the building. Okay, I said all the positive things, so maybe let's start also with the challenges. So timber has also challenges when we build with it. And the most obvious one that you all know, it is sensible to environmental exposures. What we have to do is we have to put more attention compared to conventional building materials when designing our buildings. So take moisture as an example. We really have to take care that we protect it properly from getting wet. Maybe there's a little mistake, something happens. So we also have to design in a way that it can properly dry out. So enough ventilation in case that it gets wet and we don't have any long-term problem. Important is really that we have to put more attention on the design here. Another challenge that I have not addressed with an own picture is timber burns. So we all know that. But also here, the key is that we put attention, particular attention on our design. We have to be sure that we have adequate fire safety concept in our building. We have to ensure that we prevent fire spread from one compartment to the next one. We have to ensure that we protect our connections. That's usually the most sensible part actually, because of all the metal inside these connections, that we have to protect them properly from getting too warm. And when we do that properly, I'm not very worried about fire at all. Another challenge is the variability of the material. So timber is a natural grown material. When you think now about a tree in the forest, it might not be perfectly straight, the tree. It might have a couple of branches, so it's natural. When you think now that you cut out a timber board of this tree, then this timber board will have quite many, I usually call it gross irregularities, and those affecting the mechanical properties quite much. When you think now about engineered wood products, here for example, it's a 19-meter long glulam beam then of course this variability is reduced, these properties are more homogenized, but still the variability is large. Let's look, for example, at this homogenized beam after it fails. I mean, you see the fracture pattern, you see already that's not symmetrically. You can guess that when we test another beam, that this fracture pattern looks slightly different. And you would be right. And when you test the next one, it looks again different. And all of them look different. That's not the big problem. But at the same time, not only the fracture pattern is different, also the strengths and the stiffness or the mechanical properties are different. I said before, we need reliable buildings. This uncertainty we can cover with additional safety. And efficient building. So the better we can predict these properties, the more efficient our buildings would be. And this brings me directly to research activities that we do in my research group, or that we have done. So one issue that just addressed, we work quite much on to find more efficient and further develop engineered wood products. We also have done research activities where we try to integrate other wood specimens into the construction sector, that we can also work with hardwoods. Here in Finland, of course, obviously the birch is the highest interest for us. And we also look quite much on developing structural solutions, in particular for hybrid structures, that we can use our materials more effectively. Another issue I would like to address here in this speech is construction waste. So we really have, I mean, this is something we have to do something. This is a picture from a typical construction site when it's demolished. It's taken somewhere in Helsinki. And when you look at this figure, you maybe see there is a potential of improvement. Let's keep it like this, when we think about reusing material. And also here we do quite much research, have done quite much research activities. So first of all, I want to say that the key is, and I fully agree with the speaker before me, is to extend the service life. So what we always should target, not to build anything new. The most important is that we try to extend the service life of the buildings that we already have. When it comes now to timber engineering, there are clear important issues that we have proper methods to assess the mechanical properties of existing structural existing structural components, in order to ensure a safe continuation of the service life. However, most likely we, to some extent, will also design new buildings. That will be the case to some extent. And when we do that, I think it's very important that we design them a bit more efficiently also in this respect, so that we design buildings that have the potential to be deconstructed and have the potential that we can reuse entire components, or at least the materials, effectively in maybe the next construction site. You see on the left, for example, one image, one connection that we have developed in my research group. It is a timber concrete composite connection that allows a high load transfer, but at the same time it allows to be deconstructed after service life, as one of the examples. Another thing that we have to do is to think about what can we do with all the materials that we get out from this construction site, maybe after service life. And here we should also think not only about construction waste from existing buildings, we should also think about the construction waste that we have to produce buildings. Think about, for example, a housing company, how many cut-offs they produce when they're producing their elements. And so we should think about processes, new ways, what kind of products can we produce out of this summarized waste, this wood waste, let's call it. And there we also had a couple of projects. In the middle, for example, you see a plate element that is, let's say, a hybrid between new timber board, half of them, and half of them are cut-offs from a local housing company. On the right, you see maybe a bit more artistic version of it. This is an example which is entirely produced out of cut-offs from a local housing company. With this, I came to a short summary, things that I would like you to keep from this speech. So first of all, I think you know that, but you should remember that timber is a natural material, and what you should really remember that it is most likely one of the key players for the transition, the green transition that we need to take place in the construction sector. Its mechanical properties are also very effectively. In particular, the strength properties relative to the self-weight of the material are quite outstanding. But you should also remember the other side, that it really requires a lot of expertise to design timber buildings, more expertise than for conventional material, and really a joint consideration of multiple experts to achieve this. With this, I want to thank, first of all, my research group for joining me over the last years. Thank you for this. I also want to thank my family for personal support, and I thank you for your attention.